All right, now this last topic that we're going to be covering here in our energy unit is how to calculate energy from this other data that we've been talking about. So here on page 11, we're going to talk about a couple different types of energy required to do a couple different types of things. But throughout this whole page and all of these different types of energy that we're talking about, remember that if heat is being absorbed, if heat is being added to whatever our system is, then that is an endothermic reaction or an endothermic change. And if heat is being released and coming out of our substance or our reaction, then that is exothermic. So those things still apply even though we're talking about some different situations here. Now, most of what we've been focused on have been chemical changes, and we've had some H's, and there's lots of different H's that we can have. HC stands for heat of combustion, specifically the enthalpy value for a combustion reaction. Sometimes you might also see an HRXN. RXN is an abbreviation for reaction. So it's just telling us that's the delta H, that's the enthalpy measurement for a reaction. But enthalpy isn't the same as energy. So if we want to calculate the amount of energy that is being released or gained, then we need to use this equation. Q is equal to mH. M is our mass, and H is our enthalpy there. And it will generally be given to you as kilojoules per gram. If, on the other hand, they give you a delta H value that is kilojoules per mole, then instead of multiplying by the mass, we use a very similar equation, but we can use Q equals NH, where N is the number of moles. Basically, we multiply the mass or the moles that we've got by our delta H in order to find the amount of energy that we're doing. And this is kind of similar to what we did in that law of summation. This is just a self-contained value here, calculation. Now, this is kind of a lead in to our phase change discussion, because even though we've been focused on chemical reactions so far, we can also quantify the amount of energy needed to make something change the state of matter it's in, from liquid to gas or from solid to liquid. And so we use a very similar equation here. The only difference is that this H, instead of being an H of a reaction, is now either an HF or an HV. Stands for heat of fusion, which is either melting or freezing, or HV, the heat of vaporization, where something is turning from a liquid to a gas or from a gas to a liquid. Now, generally, these values are given to us as positive values, but because our substance can either go from a solid to a liquid or from a liquid to a solid, then that direction that our substance is changing is going to determine the direction the energy is going. So once again, we come back to this idea of endothermic or exothermic. Here, if my solid is becoming a liquid, I need to add energy in. I need to add heat to make my solid ice melt into liquid. On the other hand, if I want my liquid to turn into a solid, then I'm going to have to remove that same amount of heat. It's going to be losing that amount. So sometimes you might see these as positive, sometimes as negative, and we just have to remember to make sure that those signs match what's happening with the energy as we think about those physical changes. So here, I'm going to work out a couple of quick problems with you just to help you see these types of calculations in action. Once again, if you were asked to calculate heat or energy, then that means that we are going to be looking for our Q. And here I have a mass given to me, and I'm trying to turn water into steam, reverse that. I'm trying to condense steam into water. So because that is a change between a gas and a liquid, then I'm going to be using the heat of vaporization. And this value here is the number that I'm going to use. And I'm going to make sure that I'm going to use it as a negative value, because in order for steam to turn into water as a liquid, then that is going to need to lose heat. So we're going to take our m of 5 and multiply that by our negative 2260, which gives me 11300, and that would be, actually that's joules, not kilojoules this time. You need to keep an eye on the units for energy that are in that H value there. So because that was just plain old joules, and my answer is going to be just plain old joules. In the next one, it's asking us to find our mass, and it gives us our energy, our Q, and our HV that we need to be using. So we can rearrange this equation, Q equals mH. To solve for m, we would have to divide by h on both sides to get the m alone. So m is equal to Q divided by h, and since Q is 500 and h is 21, then I can do 500 divided by 21, and that is 23.809, which, if I'm rounding this to 3 sig figs, would be 23.8. And once again, that is going to be our mass, so that is in grams. In this next problem, it doesn't actually need us to do a calculation. It gives us several different H values and asks us which would completely melt first. So I'm going to bring us back to the fundamental definition of these H's we're talking about. These H's, no matter whether it's a heat of vaporization or a heat of fusion, is a measure of how much energy is required to melt a standard amount, 1 gram or 1 mole of that substance. So down here, these numbers are bigger or smaller than each other. The bigger the number is, the more energy we need to add to that substance in order to cause it to melt or boil. So if I want to figure out which one is going to melt first, then if I'm adding the same amount of energy to each of these, then it's going to, the one that melts first is going to be the one that has the smallest H value, the one that needs the least amount of energy in order to melt. And the one that is going to melt last is the one with the biggest H value, one that needs the most energy before it can change states. So that is our heat of vaporization and heat of fusion, our simple phase change calculations. And to finish out the page, we're going to now talk about some calculations that we use when the temperature is changing. So these are two completely different types of calculations. And honestly, what I look for when I see one of these calculations on the next page is I ask myself, is something changing temperature? If it is, then I need to use this equation. If it's not, it could be a physical or a chemical change, but either way, we're using that Q equals mH equation, so it's pretty simple. Now this equation is very similar to the last one. Q is still heat or energy, either way, and M is our mass, and of course delta T is our temperature change or change in temperature. And then we have this C value. C is our specific heat capacity. This is kind of like that H value. It tells us how much energy is needed, except this time it's how much energy is needed to make a substance change temperature instead of making that substance change phase. So a low specific heat capacity means that I don't need much energy to make the temperature change. So the temperature will change faster or more than something that has a larger specific heat capacity. That means that they have a bigger capacity. They can handle more heat and contain more heat before they have to change temperature. So if we add the same amount of heat to all of them, then the temperature change will be slower the larger that specific heat is, or overall it will change less temperature because it can absorb more heat before it changes. So this is something you need to be aware of, and this is on our equation sheet. The specific heat of water is 4.184, and we need to be able to use that in our equations in order to be able to calculate any of these variables. So the next couple of problems are just a couple different variations of using this equation. And real quick, before we do them, I want to help you rearrange this equation a little bit with a quick reminder of this general idea. Whatever variable I'm looking for, whatever my x is going to be equal to the opposite side over its neighbors. Now, we don't need to use this to solve for q, because we already have an equation for q. We just need to multiply m times c times delta t. But no matter what else I'm solving for, if I wanted to solve for m, then its neighbors is everything else, c a, and then c delta t. So I'd be dividing q by c and delta t, because that's how I would cancel those out on this side. So m equals q over c delta t. If I was trying to solve for c, that'd be q over m delta t. If I was trying to solve for delta t, then that'd be q over mc. It's basically everything that's on that same side with whatever we're trying to solve for is what we're going to be dividing by the opposite side by. So that is our generic equation. And in this first problem, it asks us to calculate heat. So I am looking for Q, and then it says required to warm 750 grams of water. That's my mass. And it tells us we want to turn it from 10 degrees to 80 degrees. That's a temperature change. And this delta T is how much I want my temperature to change. So it's not the 10 or the 80. We have to subtract those two from each other in order to find that our delta T is going to be 70 degrees Celsius. So we have M, we have delta T. We need to remember that because this is water, I can and should use this as my C. So Q is equal to M times C times my delta T, and multiplying those all together gives us 219,660, and I would need, I guess I didn't include all my sig figs here. This is 3 sig figs because I had a decimal place on each of those, so this should be 70.0. So 3, 4, and 4, so I need to round this to 3 sig figs here, which means my final answer is going to be 2, well, this really looks like 2 sig figs. I could put this into some scientific notation and say this is 2.20 times 10 to the 5th, and that would be 3 sig figs, as well as making sure I have joules as my units for energy. But we generally would give you more sig figs if we're going to give you a number that ends up that big, because we want precise numbers, precise measurements. It's not just us trying to get around giving you hard problems. It's that in the normal scientific world, we wouldn't do a calculation like that if we couldn't get more precision from it. So in this next problem, it asks us to find the specific heat capacity. That means we're going to be solving for C. So I need Q and then M and delta T here. And so looking through, I have my Q here, and my 10 grams is my M, and I'm going from 42 to 35, so I want my temperature change here to be 7 degrees Celsius. And when we plug all of those numbers in, make sure that in your calculator you're dividing by the M and the delta T. Even though they're on the bottom and being multiplied together, you either need to do that multiplication first, or you need to use parentheses around that denominator like I have here. Now, if we have plugged this into our calculator correct, and I would highly encourage you to do so, make sure that you can push the buttons, then our final answer here is 0.2914, technically, although 2 sig figs is what I'm going to be limited to, so 0.29. And our units for specific heat are actually a little bit complicated, but we can always just make them match that Q for our water. So it's joules over grams over degrees Celsius. It's basically all of the units for all of these things Q was in joules, M is grams, and this is degrees Celsius. It's like we just did math with those units as well, just all combined together there. And last but not least, we want to calculate the mass of water that is going to undergo a chemical or a temperature change. So opposite over neighbors means now I'm going to take this Q and this temperature change of 10 degrees Celsius, and this is still water, so I'm going to be using that same delta, or that same C, and plug in all of those numbers in. Ooh, actually, I'm noticing that my joules in my specific heat here don't match the kilojoules that I suddenly have there. Almost everything today has been joules, and we do need those units to match. So I'm going to go ahead and turn this into joules, just like kilometers into meters. I would multiply by 1,000. So this is 9750 joules, and then our C is 4.184, and our delta T is 10. So if we do that math, 9750 divided by 4.184 and divided by 10 is 233.03, and I would need this, how many sig figs? Yeah, I should have kept that 0.0. That's 3 sig figs there. So I can round this to 233, and this is our mass, so this is going to be grams. So hopefully these calculations aren't too hard. Really what we need to be able to do is tell when to use each equation. So look for that temperature change. If it's giving you temperatures changing, then that has to be this equation. If it's not, it's Q equals mH. So we'll build on this in class next time. Hope it's not too hard on its own.